Hi everyone. Thanks for joining us today for this public webinar about several projects that the U.S. National Science Foundation supports that monitor and predict the future of our oceans. My name is Lindsay Martin. I'm an ocean policy specialist at NSF, and I'll be introducing this event today on behalf of NSF's Division of Ocean Sciences, and I'll also be moderating any questions that you have. While you're here, you'll be muted and your video is off, and you can use the Q&A function on the bottom to submit questions. So, a little bit of background on, how NSF monitors and studies the oceans. So, while the Division of Ocean Sciences was, sorry, my dog's a little happy. Lay down. So the Division of Ocean Sciences was officially created in 1975. NSF has been a leader in basic ocean sciences since it was first established in 1950. Now, 4 of NSF's first 100 awards were actually related to ocean science. These early programs included monitoring carbon dioxide levels and radioactivity in seawater and studying Arctic oceanography and sea ice. Both of these subjects are studies that provide really important baseline information to our changing climate. So NSF has been this leader in basic ocean science since it was established for the past 71 years. And we've supported and funded cutting-edge ocean science technology that drives fundamental research and innovation that helps make new discoveries about our oceans every day. In addition, NSF has provided important ocean science resources like the academic research fleet of ships and submarine vehicles that are part of the National Deep Submergence Facility. This year, we are celebrating the start of the UN Decade of Ocean Science for Sustainable Development. The UN Ocean Decade was established to recognize this opportunity to reverse the decline in ocean health that we see today, while continuing to rely on the ocean for our ever-increasing needs, particularly as the climate is changing. The Ocean Decade has endorsed 5 NSF efforts as official Ocean Decade actions. So we have the Navigating the New Arctic Program, which brings together research across social, natural, environmental, computing, and engineering sciences to inform our understanding of Arctic change and its both local and global impacts. And this really creates new directions in Arctic science and technology, which in turn strengthen everybody's economy, security, and resilience within this really important region. We also have the International Ocean Discovery Program, which is an international marine research collaboration that explores Earth's geological and environmental history, using ocean-going research vessels that collect sub-seafloor sediments and other environmental samples. The third is the Coastlines and People Program, which supports these multi-institutional hubs where these diverse, innovative projects that focus on critically important coastlines are fostered alongside local relevant stakeholders. Now, one of the themes of the UN Ocean Decade is a predicted ocean. And 2 of the endorsed programs play a really major role in monitoring our oceans and predicting their future. And those are 2 of them we're going to be hearing about today. The first is GeoTraces, which is an international program collecting data on trace elements in the oceans. Now, trace elements are rare chemicals that play very important roles as essential nutrients. They act as tracers of processes now and in the past, and they affect organisms as toxic contaminants. The second one we'll be hearing about is the Global Ocean Biogeochemistry Array, or GOBUGC, which is contributing 500 robotic floats that collect chemistry and biology data from the ocean surface to up to a mile deep. This really allows us to transform how we observe the ocean, predict the global effects of climate change, and understand ocean biogeochemical cycles, carbon uptake, acidification, deoxygenation, and ecosystem health. It's a lot of subjects that we can cover with just one observation point. We'll also be hearing about 2 other pieces of infrastructure that we use to research the ocean. The Ocean Observatories Initiative, or OI, is an ocean-spanning network of surface and deep ocean sensors that help us to gather essential information. We'll also hear about the National Deep Submergence Facility. This is a collection of submarine vehicles, including the famous Alvin, that allow us to explore and study some of the deepest parts of the ocean. So to start our program today, let me introduce Dr. Phoebe Lamb, who will tell us about the GeoTraces program. Dr. Lamb is an associate professor of ocean sciences at the University of California, Santa Cruz, where she studies the biological and chemical cycling of elements in the ocean. Prior to that, she was on the scientific staff of the Woods Hole Oceanographic Institution and was educated at UC Berkeley, Princeton, and MIT. She was a member and then co-chair of the International GeoTraces Scientific Steering Committee from 2012 to 2020, and she continues to be active in the US and international GeoTraces activities. She co-led the 2018 GeoTraces expedition from Alaska to Tahiti and will co-lead a second expedition in 2023 to the Amundsen Sea near Antarctica to study the impacts of melting glaciers on the chemistry of the ocean. So, Dr. Lamb, whenever you're ready, go right ahead.
Thanks very much. Let me share my screen. Okay, well, thanks very much for having me, and I'm thrilled to be telling you about the GeoTraces program. So the GeoTraces program is an international study of sorry, let me just change my windows here. Sorry. It's an international program whose mission is to map the distribution of what we call trace elements and isotopes in the ocean. So a trace element is just, as Lindsay said, just an element that is found in minute quantities. But just because it's small concentration doesn't mean it's important. So I'm going to tell you a little bit about why these elements are important and why it is that we're measuring these in the ocean. So the first category of elements that we study would be called the nutrient elements. If you look at the back of your vitamin bottle, you'll see some of these elements listed in the back of your vitamin bottle. So these are elements such as iron, zinc, and manganese that are essential for all life, including our lives, which is why it's in our vitamin bottles. So we want to understand why the distribution of these elements in the ocean, where they come from, and how fast they're getting there, and how fast they're being taken away. Another class of elements that we study in the GeoTraces program are toxins. You probably have heard of mercury in the ocean or lead in the ocean. Both of these are neurotoxins. They come from, as a result, sometimes of human activities, sometimes of natural activities. And these affect both the food webs and have consequences for human health. A third category of elements are what I'm calling here the indicator elements. They may not be elements that you're as familiar with. Here I've listed 3, beryllium, radium, and thorium. But they're elements that we use that tell us the rates of things. So whereas we can map out the concentrations of those nutrients and those toxin elements that we care about, we really want to know how fast it is that they're getting there. And these indicator elements can help us figure those out and quantify those rates. Other indicator elements that I haven't listed here include iron isotopes or other elements and radioisotopes. These give us very important fingerprint information about what biological processes might have affected the elements we do care about, the nutrients and the toxins, as well as what chemical processes or physical processes might have processed them. And they tell us where they might have come from. The power of GeoTraces is the fact that we measure all 3 categories of these elements on every single sample, on every single cruise, from the surface all the way to the deep ocean. And the idea is that measuring the total, all of these elements, it gives us information that is much greater than the sum of the parts. For example, we do care about the nutrient and toxic elements, but we can't predict the future ocean unless we know the rates at which these elements are being transported and transformed within the ocean. And that's what the indicator elements are for. By combining all 3 categories of elements together, we truly get a much deeper and richer understanding of the chemistry in the ocean and the biological and physical consequences for the future. What I'm showing you here is a satellite image of mineral dust that is blowing off of the Sahara into the North Atlantic Ocean. Even though this is not what the exact dust event I'm going to tell you about, there is a lot of scientists think that increased dust events in the past, especially to the Southern Ocean, profoundly affected the biology of the Southern Ocean and increased the phytoplankton's growth rates that were living there. And that had profound effects on climate. And so since we know that this has had a profound effect on climate in the past, we're pretty sure that this is going to have an effect on climate in the future. And so this is one of the reasons why we're so interested in understanding the distribution and the rates and the delivery of these trace elements to the ocean, because they can have such profound effects on the climate. So iron, for example, that I just mentioned, that is brought together by mineral dust, by understanding the distributions from our geotraces measurements and by understanding the rates using these indicator elements, we are then able to incorporate these into global climate models in order to understand how the ocean and then therefore the planet will respond to changing climate. But iron is hard to measure. Trace elements are hard to measure. The reason that they're hard to measure is they're in really small quantities. So imagine the amount of metal in a paperclip. Now imagine dissolving that paperclip into 30 Olympic-sized swimming pools. That's the concentration of iron we're trying to measure. So it's very small. And then some of the other elements that we measure are in even smaller quantities. Now imagine trying to measure that amount of iron from a somewhat rusty ship. All of our ships are made out of metal. The seawater is a harsh environment and does make basically all of our ships rust. And we're always fighting that. And so how are we going to measure these really minute quantities of elements from these platforms? Well, it means that we trace metal chemists have to be much more careful than even your typical oceanographer who already goes through heroic efforts to sample from the ocean. The way we do that is by having specialized equipment. So we've modified our sampling equipment to minimize the amount of minimize the amount of metal that is in the sampling equipment. We use cables that are made out of non-metallic materials instead of the standard steel wires. Once we collect our samples and bring them aboard, we run around and we put shower caps on the tops of the bottles. So each of these is a bottle holding about 10 liters of seawater, and we've covered them with shower caps to protect them from contamination that could be coming, say, from the soot of our smokestack of the ship. That's still not clean enough, because once we've covered it, we still want to get it into an even cleaner environment. So then we take these bottles off. Each one of these bottles contains water sampled from a different depth in the ocean. We carry it into what this is, a lab clean van. And so this is a container that has been modified to become a lab, that has been further modified to have almost no metal in it, and has been further modified to have only filtered air blowing into it, so that we have a very clean environment with no rust and no internal sources of contamination. Once we bring the sample bottles in, then we can rack them up, and then we have our very hardworking super techs that can patiently sample this water into hundreds and hundreds of sample bottles. Here they are sampling just into a couple here. Because these sample bottles will be distributed to dozens of PIs and scientists and graduate students and postdocs who will make these measurements of all of these different indicator, nutrient, and toxin elements that we measure on geotraces. Once we get the samples, we bring them, there are other ways of collecting the samples that we need. I won't show you them all, but I'll show you a couple. Here we have these in situ pumps, again on non-metallic wire that filter thousands of liters of water. We collect particles onto filters and then bring them in and analyze the chemical composition. These cartridges filter some of those indicator elements and grab them out of seawater, including radium. This is an example of aerosol sampling devices that we show, that we mount on the bow of the ship. They only turn on when there's clean air coming from the ocean, and they turn off when there's smokestack air, for example, that's blowing towards them. And so this is how we can collect aerosols in the atmosphere, which is one of the main ways in which trace elements can get into the ocean, as I showed with that satellite image of the dust. Once we have our samples, which we've painstakingly collected very cleanly, we bring them into our clean labs. So we construct clean labs on the ship. We use this plastic sheeting material, and we create these bubbles. We put air filters in so that, again, we're only pumping in clean filtered air. And then we have this now nice clean environment within a dirty ship in which we can process our samples. So once we've built these bubbles, then we can process our samples and feel quite confident that we won't be contaminating them with any of the rust that's prevalent on the ship. Some scientists analyze their samples at sea. Other scientists bring their samples back home and analyze them in the lab because their instruments can't go to sea. Regardless of how scientists measure their samples, we take great efforts to make sure that everyone can get the same number, and we do extensive what we call intercalibration exercises. And so we have scientists, this is an example of a mercury intercalibration exercise in which scientists from around the world brought their instruments to one lab, set them up side by side, collected the same water, and then tried to analyze it and get the same number. And if you get the same number, then great. Then we feel confident that no matter who's making those measurements, we're going to get the right and comparable number, accurate number. If the answer isn't right, then we help each other. We help each other get the right number, because one of the really important tenets of geotraces is we're trying to build capacity so that more people around the world can make these measurements, so that we can continue doing this and understanding how the ocean works. And this is an international effort. We've got scientists from 35 nations involved, from every inhabited continent in the world. We have to make sure that the data from one country is comparable to the data from another country, because we're going to ultimately, and we are ultimately putting together all of this data into a single global atlas that is freely accessible to everyone. And it has to be a global effort because no single country can do this alone. These measurements are painstaking. It's hard to collect the samples, it's hard to measure the samples, and no single country has the resources to do it. So we need to leverage the energy and the know-how and the resources from all these different countries in order to cover the globe. This map shows you the transects, the lines in which we are crisscrossing the ocean with in order to sample for geotraces. The yellow and the black lines show you the transects that we've already completed, and the red ones show you the ones that are still to come. We've done over 100 cruises so far with research vessels from 19 different countries. This, I just wanted to highlight the cruises that the U.S. geotraces community has accomplished with U.S. vessels. We've done cruises in the North Atlantic, in the South Pacific, in the North Pacific, in the Arctic Ocean, and we will be doing some in the South Pacific and in the Antarctic in the coming years. We are going to all places all around the world, and we're sampling in regions of the world experiencing rapid climate change. So, for example, in 2015, three nations mounted geotraces expeditions to the Arctic, including Canada, Germany, and the U.S. And we all went to the Arctic at the same time because we wanted to cover the entire Arctic, and we wanted to get a view of the entire Arctic in that year. We also had this great opportunity for two of the ships to actually meet. So here's a photo of the U.S. ship, the Healy, and the German ship, the Polarstern, meeting at the North Pole. We happened to get to the same place at the same time. This was about halfway through our 2-month voyage, and so we got to meet each other. We got onto the ice and visited each other on the other ship. These were the first people that we saw that weren't the people on our ship in a month, and so it was a really nice morale boost to see our colleagues. I even got a spare part. I had an instrument that was broken on my ship, and I got a spare part from my colleagues on the German ship. Besides being this great morale boost and great photo opportunity, it also had a very important scientific function, because this was the perfect intercalibration where we could both sample from the same place using different platforms, different instruments, different analysts, different instrumentation, but we brought the data together to make sure that they were comparable, and they were, and those data will be coming out in our next data product release, which is just in a couple of months. So despite this happy historic meeting, though, there were constant reminders that climate change was happening. This was the first time that a U.S. ship made it to the North Pole by itself. In the past, U.S. ships had made it to the North Pole before, but they had to have 2 ships in order to have enough fuel to break the thick ice. But because the ice had been melting so quickly, it was thin enough that a single ship could break it, and we were able to make it ourselves. So it was a bit of a dubious, sort of bittersweet accomplishment, and a reminder of what we're up against. Our science also showed that the climate is changing. One of these indicator elements, radium, was found to be 2 times higher in concentration in 2015 than just 8 years prior. And radium is one of these elements that comes from the coastal zone. And the idea was that the ice had melted and retreated so far from the coastal zone that there was a lot more wave action that was stirring up chemicals from the sediments, including radium, including other things like iron, and bringing those chemicals into the center of the Arctic. So we had evidence, direct evidence, that not only was the ice melting, but it was affecting the physics, that was affecting the chemistry, that was likely going to affect the biology. In a few years, we'll be going down to Antarctica. We'll be studying the impact of melting glaciers. Now, glaciers are slightly different than sea ice because they're formed on land, and therefore when they melt, they affect sea level rise. But they also affect, like in the Arctic, they affect the chemistry and the biology of the ocean. And so we'll be going in 2023 to look at those impacts. So one of the hallmarks of GeoTraces is that we're putting together all of this data into a single atlas and a single data product and making it available to the world. Anyone can go and explore this data, create these beautiful distributions, pick elements that they care about, places that they care about, look at the data, teach it, learn from it, and then share it with their colleagues. And so what we want is for people around the world to use our data and to put it into their models and be able to better predict how the ocean is going to react to climate change in the future. So GeoTraces is an international program. We're building capacity to continue making these measurements. We're measuring all of our nutrient, our toxin, our indicator elements. These are helping us understand the key biological and chemical processes in the ocean that will help us understand and predict the ocean and our planet to come. So thanks very much.
Thank you very much, Dr. Lamb. If anybody has any questions, feel free to submit them into the box. If not, we'll move on. But if you do have a question, feel free to put it in there and we can always type our responses. Got a question. So aside from climate change, what other areas of application does the GeoTraces program have?
Lots. GeoTraces also helps us understand just the basic functioning of how the world works, how the ocean works. There are a lot of processes like the circulation of the ocean, the way the biological production works, the source of these nutrients to the ocean, that just allows us to understand the functioning of ecosystems, both coastal and the open ocean in all sorts of different places. And the measurements that we make in GeoTraces really just help us understand the functioning of the earth, the functioning of the ocean, and that allows us to, if you have interest in fisheries, for example, this will help you understand the base of the food web and how that is set up. If you have interests in circulation, some of our measurements are helping us understand the circulation better. So there's lots of basic and also applied consequences to our research.
Good to know. One more question. How can early career researchers in marine geochemistry who are new to GeoTraces, so with no existing networks, how can they join these research projects and potentially participate in future cruises?
That's a great question. We are always looking to train the next generation. So the first probably the best thing to do is to join our email list. Go to geotraces.org. You'll find lots of information there. You can sign up for the email list. We have summer schools for people who are new to the program. They can learn about the techniques. They can learn about the science. If you are an undergrad thinking about going to grad school, look at the research that's happening and think about going to grad school to learn about these things. Contact us. If you're interested in doing this research, look at the research that's happening, who's writing these papers, and just send an email. We're always glad to invite new people into our network.
Thanks. Thank you very much. I think there are a few more questions in the box. I'll let you type their answers if you want. We're going to move on to our next presentation. So let me introduce Dr. John Trowbridge, who will be telling us about the Ocean Observatories Institute. Dr. Trowbridge is the principal investigator of the OOI, which is funded by NSF and maintained in a partnership of the Woods Hole Oceanographic Institution, University of Washington, Oregon State University, and Rutgers University. He currently serves as president of the board of directors of the Northeastern Regional Association of Coastal Ocean Observing Systems, which is a component of the Integrated Ocean Observing System. He's previously served as chair of the Department of Applied Ocean Physics and Engineering at the Woods Hole Oceanographic Institute, and his research interests include coastal physical oceanography, coastal engineering, and ocean observing. So without ado, go ahead and take it away.
All right, thank you very much. My name is John Trowbridge. As I said, I'm the lead PI for the Ocean Observatories Initiative. Our tagline is sustained data for a changing ocean. And I'm presenting on behalf of the OIPI team, who are listed here. Next slide, please. I'll talk a little bit about the OI vision, then I'll describe the research arrays that we maintain and a few scientific results, and then I'll end with a little bit about resources. Next slide, please. All right, the OI vision is real-time data from more than 800 instruments to enable research and education in earth and ocean sciences. There are 6 interdisciplinary science themes that have recently been articulated in an updated science plan that was released late last year. We have marine arrays at 3 scales: global, regional, and coastal. All of these are united by a common cyber infrastructure that ingests data from all of the sensors, processes it, quality controls it, and serves it in near real time to anyone with an internet connection. The envisioned lifetime is 25 years. This program is sponsored by the National Science Foundation, and it's operated and managed by a partnership of Woods Hole Oceanographic Institution, University of Washington, Oregon State University, and Rutgers University. You can see on the right the arrays that are maintained by the Ocean Observatories Initiative. Starting in the Pacific, we have Station Papa in the Northeast Pacific, the regional cabled array and the coastal endurance array off Oregon and Washington. Off Greenland, we have the Army Sea Array. Off New England, we have the Coastal Pioneer Array. And then in the Southern Hemisphere, we have the Global Southern Ocean Array and the Global Argentine Basin Array. The 2 Southern Hemisphere sites have been discontinued, but we continue to serve data. All of these sites were selected by more than a decade of planning, community-wide, by the oceanographic and earth science communities to address the most pressing scientific questions. Next slide, please. The regional cabled array is shown in this diagram. There's a cable that extends out from the coast at Pacific City, Oregon, and there are 2 branches. One goes straight west to access Seamount, which is volcanically very productive, and the other branch goes out over this slope and then back up onto the shelf where it supports the endurance array. There are 900 kilometers of fiber optic cable that provide power and bandwidth for 2-way real-time communication and data flows. This is like having a laboratory capability on the seafloor of the ocean. There are more than 150 core instruments, and then there are also multiple instruments that PIs external to the program have added. So that's a capability that's offered. Some important scientific advancements were observation of the 2015 eruption of axial seamount, a very nice paper on the tidal triggering of earthquakes based on data from this array, some observations of methane seeps, and some remote observations of marine mammals based on acoustics, which are particularly important for COVID during this quiet ocean phase. One exciting thing to me is that there's actually an eruption predicted on the basis of the seafloor observations at axial around 2023. And in my understanding, this is perhaps the only place in the world ocean where an eruption can actually be predicted on human timescales. This array enables research in fundamental geophysics. There are unique ecosystems at the seafloor that are observed with this system, and it also informs tsunami hazards. And this is operated by the University of Washington. My co-PI, Deb Kelly, leads this. Next slide, please. The Global Erminger Sea Array is motivated by important processes impacting climate. You can see in the cartoon on the upper left, thermal haline circulation. The Erminger Sea is one of only a few sites worldwide where there's deep water formation. This is caused by outbreaks of cold air from the Arctic that cool the ocean water rapidly and cause it to sink and take the northward flowing warm water, turn it into deep water that then flows southward and feeds this complex thermohaline circulation that regulates the ocean climate. It's been hypothesized that this deep water formation might change or even cease because of the melting Arctic, which creates a competing effect of fresh water, which is light. And therefore, this is an important place to observe for decades to understand this phenomenon. The other phenomenon of particular importance is shown in the cartoon on the bottom left. This is CO2 sequestration. There are plankton blooms that are formed during the summer by the intense solar heating. There's an opportunity for CO2 exchange between the atmosphere and the ocean. But then in the wintertime, there's deep mixing that takes the particles downward. And so it's this competition between the bloom in the summer and the deep mixing in the winter that determines whether it's a net source or sink for carbon from the atmosphere. The array is shown on the right. You can see there's a surface buoy that has air-sea flux instrumentation to measure the air-sea transport of heat, momentum, moisture, and gases. And then there are moorings and vehicles in the water column. And all of these data are transmitted back to shore by satellites in near real time for processing and data delivery. Some firsts here, the first year-long measurements of deep water formation at this site. It's very difficult to maintain a buoy at these high latitudes, primarily because of icing, but also because of the strong forcing. First year-long measurements of air-sea heat exchange and the biological carbon pump, which will inform future research. And as I said, this site impacts fundamental climate science with strong societal impacts. And this is operated by Woods Hole Oceanographic, and the leader is Al Putin. Next slide, please. Global Station Papa is in the Northeast Pacific. It's a site with high nutrient, low chlorophyll. It's vulnerable to acidification, deoxygenation, and marine heat waves. There's a very productive fishery there. It's impacted by a number of processes, including the Pacific Decadal Oscillation. One interesting thing about this site is that the low eddy variance permits approximately one-dimensional balances that enable process studies. And this has been the site of process studies, particularly including a NASA program called Experts. Next slide, please. The Coastal Pioneer Array is off New England, and the left image shows satellite chlorophyll. And you can see the contrast between the very highly productive shelf in green and the lower productivity in the deep ocean in blue. The Pioneer Array is that square black box right at the boundary between the two, at the shelf edge. And an important question of this site is how mass and momentum and heat and nutrients are carried between the deep ocean and the shelf. The nutrients in particular feed one of the most productive fishing grounds in the world. And you can see some of the eddies and filaments that accomplish that transport in the image on the left in the chlorophyll. And the array, which is shown in the upper right, is designed to capture that complex spatial and temporal structure. There are two lines of moorings that extend across the outer shelf and the upper slope. And those moorings measure the water column properties as well as the air-sea transport. And there are also vehicles that transit the region to fill in the information between the fixed moorings. This array has resulted in two newly discovered physical mechanisms for shelf ocean exchange that could only have been obtained by the combination of satellite imagery plus the in-situ data that the OOI provides. One surprising outcome has been the dominant and rapidly evolving role of the Gulf Stream. The Gulf Stream generates rings that that penetrate northward and impact this region, and they sweep warm, salty water laden with nutrients up onto the shelf. And this is a new feature. It's just been changing in the last decade. It happens in other places, but it hasn't happened in this place until the last few decades. So this is a rapidly evolving system. The Gulf Stream water up onto the shelf has big impacts on ecosystems, fisheries, and also because of the air-sea temperature difference on hurricane and storm intensities. The Pioneer Array was envisioned as a movable array. It's been at its present site since 2014, and it's scheduled to move to a new site just north of Cape Hatteras in 2024, where it will be reconfigured to address a new set of questions. Next slide, please. The Coastal Endurance Array is off Oregon. You can see the array schematic on the right. There are two lines of moorings, one north of the Columbia River, which is the largest outflow of fresh water on the Pacific coast of the U.S., and one south of the Columbia outflow. In addition to the mooring lines, there are gliders that transit the water column. All of these data, again, are transmitted back to data in real time by satellites. There are important processes, including ocean heat waves, hypoxia, and ocean acidification that have been observed by the system. There have been new insights into the proper interpretation of satellite measurements based on in-situ measurements that have been provided. And there are numerous impacts: the Columbia River, California currents, winds, forcing, El Nino, and the Pacific Decadal Oscillation that impact these places. This is operated by a combination of Oregon State University and University of Washington. Next slide, please. We have a number of resources. First of all, the fundamental thing that this program provides is data. So there's data access on the OOI website, oceanobservatories.org. Also on this website, there's a list of the publications that have been enabled by OOI data. And you'll see that people around the world are using this data from multiple countries on 5 continents, from numerous academic institutions. So this is a place where you can find out about the science that's been done in addition to accessing the data. There's a help desk function, help@oceanobservatories.org. Our primary mission is scientific, but third parties have been taking OOI data and using it for education. I've listed 3 here: University of Washington, the Data Lab program at Rutgers, and then the Project EDDI program at Carleton. All provide educational modules of various kinds, primarily focused on an undergraduate education that can be used to inform the next generation about important oceanographic processes. The National Science Foundation has funding for OOI-related conferences and training, and you can find that on the NSF website. We have a presence on social media, and there's a discourse platform on our website where we can communicate with the community. Next slide, please. That's the end of my presentation, and I'll be happy to answer any questions. Thank you.
Thank you very much, Dr. Trowbridge. We have a question coming in from the Netherlands. So in the Northeast Pacific, there's also the ONC Neptune Array. This person's wondering if Station Papa communicates with that system.
Station Papa is pretty far offshore of the Neptune Array. So there's no, the Neptune cable does not extend out that far. But there's certainly scientific collaboration between the OOI program and the Neptune program, which is managed by Ocean Networks Canada. And we share, I serve actually on the advisory board for the Neptune program. And we share best practices, we learn from them. And we share data, and we sometimes share shipboard operations. For example, our gliders are sometimes managed by Ocean Networks Canada.
That's great. It's a perfect example of the international collaboration that has to happen when we're doing ocean research. Another question coming in. So how do you plan to carry developing countries along with this initiative? It seems that this area it's new, but it's also very resource intensive.
One way that we carry developing countries along is by providing data to everyone who has an internet connection worldwide. And so people from any country can pick up our data and use it for whatever purpose, for teaching, for research. And I think that's the most fundamental way that we would bring developing countries along. The educational modules that I mentioned presumably would also be used in developing countries. As was mentioned in the question, the infrastructure itself is very expensive. It's expensive to purchase and it's expensive to operate. The ocean is a very harsh environment, particularly in some of these extreme sites that we're trying to operate, top of a volcano, year-round presence off Greenland and so on. So I would say that the contribution that's being made here is maintaining the infrastructure in those sites and serving the data for everyone to use for their research or education.
Thank you very much for that answer. Yeah, it really highlights the need and importance of open data, especially in the future. All right, well, thank you very much. Our next speaker is Dr. Joellen Russell, who will be talking about the Global Ocean Biogeochemical Array. Dr. Russell is the Thomas R. Brown Distinguished Chair of Integrative Science and professor at the University of Arizona in the Department of Geosciences. Her research uses global climate and Earth system models to simulate the climate and carbon cycle of the past, present, and future. She currently serves as co-chair of NOAA's Science Advisory Board's Climate Working Group. And before joining the University of Arizona, Dr. Russell was a research scientist at Princeton University and NOAA's Geophysical Fluid Dynamics Laboratory. Dr. Russell actually grew up north of the Arctic Circle in a very remote fishing village and has actively been working towards her current position since the age of 12. And she can't believe that she gets paid to work on this biggest challenge of our time, climate change. So with that, please take it away, Dr. Russell.
Thank you, Lindsay. That is exactly true. I am so delighted to get to talk to everybody here about this amazing work that my colleagues and I have had the opportunity to basically press forward on these boundaries. It is so important and so exciting. And I just want to remind everybody, pale blue dot time, this is planet Ocean, right? We are a blue planet. 72% of the Earth's surface is water. It's our ocean. And it's been very inaccessible for much of human history because you can't just walk on out and check out a rock now, can you? And so we've been working really hard as oceanographers, as a community, both in the US and in international collaboration to try and get a handle on what is changing about our oceans. And what you're seeing right now, that is not satellite data. This is a simulation. And to quote the acting chief scientist of NOAA, Craig McLean, if you like your weather forecast, thank an oceanographer. This is FB3, the latest and greatest from the National Oceanic and Atmospheric Administration. And this is the model that predicted whether or not you needed to bring an umbrella this morning. In my case, whether or not my kids could play outside because they might get heat stroke here in Tucson. No, it's really true. And things are getting warm in here. With all of the increased CO2 that we're adding to the atmosphere, where is it going? And how long is it going to hang out in the atmosphere? And how hot are we going to be? And can we predict this well enough to know what's going to happen next and make wise decisions as citizens of the world, right? This is, okay, here's our global atmospheric temperatures, but I know most of you have got to be oceanographers, right? So I'm going to show you how much of that heat is going into the ocean. It's 93% of that excess energy that's not getting back out of our planet's atmosphere. That 93% of that is going into our ocean. That tiny pink line here along the bottom, that's the warming in the atmosphere. The warming in the ocean is even bigger, 93% of that right here. And so many things are changing. And so there's this UN Decade of the Ocean, Science for Sustainable Development, that basically the whole world is participating in to try and get a handle on the changes and try and work together towards a healthy, sustainable ocean. It's so important. There are so many different things. And let me tell you how the Global Biogeochemical Array of floats is helping with this. Those floats are on the front line of how we predict and monitor our ocean. It's so important. Okay, I'm going to take one tiny little minute about why we need to know how much carbon's in the ocean and how it's changing. Actually, nationally, just because I'm, here's a US audience as well as an international audience, it's actually the law. The Supreme Court ruled in 2007 that the Clean Air Act does in fact require the United States, the EPA, on behalf of the United States, to regulate carbon dioxide as a pollutant. It's the law. Okay, majority decision. Woot, woot. But actually, they only cited one brief in their ruling, and it was the brief written by the scientists. And I have to confess, I'm one of the 13. Tag. And in addition, we have global agreement on what we should be doing about all that carbon dioxide, which is amazing. Hello, Paris Agreement. But what's actually happening and what we can do about it will depend on where things are going. So about 46% hangs out in the atmosphere of everything we burn, and about 23%, so 1 out of 4 carbon molecules that comes out of your tailpipe anytime you drive your car goes into the ocean within a year. 1 out of 4. 1 out of 8 goes in around Antarctica. I know, wild, right? 1 out of 4. So what we need to do is reduce the uncertainty in how much carbon is going into the ocean, when, and by what process. So important. Okay, and here's something that's also a little bit worrying me, is that we need to verify too the effectiveness of any ocean-based carbon dioxide removal. We got a lot of people saying a lot of things about how much ocean carbon could be, how much the ocean could do, and sure, there won't be any side effects, and it'll stay in there. I want proof. I would like evidence, right? Being a scientist, it's important. It's going on right now. So ocean carbon uptake is the challenge for oceanographers of our age. This we must know. We must know it's important to every single person, all 7+ billion of us on planet Earth, what happens next. And we have to do it in a changing environment. We can't just assume the ocean's sitting still and go visit it with a ship every once in a while. It just won't work, because I don't know if you can see behind me, that's a simulation based on winds and ocean carbon gradients of how much carbon is going in or out of the ocean at any given minute. Can you imagine how hard it would be to get the budget given all of that mess and this increasing winds? Everywhere it's red is where there's increasing winds. Yeah, the whole thing. And that's driving deeper mixing. And this is this fantastic paper by J.D. Sally. Basically, everywhere it's blue is where the mixed layers are getting deeper in the ocean. I know. Shock. And like, oh boy, we better get on this, right? And I'm just showing it to you again. This is air-sea carbon flux. And the wind vectors, which you can see on top of it. Red is where it's outgassing, blue is where it's ingassing, and this is done a NASA visualization, Shira et al. From 2020. Gosh, isn't it gorgeous? And this is what we're trying to do, is move from just our ships, which are critically important, as Phoebe was telling us all, so important, this work. They take months. My longest cruise is 56 days away from my family, out in the ocean, working 12 hours a day in, day out. Every second you could put into getting more measurements, because this is your only shot to get them, right? You got to move. It's so important, but it's hard and it's dangerous. And there aren't very many of us. There are only, HEU tells us there's only about 6,000 research PhD level oceanographers in the world. 6,000 out of 7+ billion people, and we're responsible for all of this. I know, it's crazy. And thank goodness the NSF is here to help us get there and get it done. So this is the measurements from ships from 1999 to 2015. Look at all the white space. There's a lot of white space, and if this is what's going on, how are we going to get there? Robot floats. That's how we're going to get there. And this is Argo. This is the physical temperature, salinity, pressure measurements made by Argo floats starting in 2004. What an extraordinary increase in the number of measurements. And we've got biogeochemical ones with pH, nitrate, oxygen, and chlorophyll sensors, optical sensors on them through the Southern Ocean Carbon and Climate Observations and Modeling Project, which is primarily funded by polar programs at the National Science Foundation. Thank you to, if you like your forecast and you want to know what the ocean carbon uptake is, thank Peter Mill and Polar Programs, because this is what we're doing with the money that they invested in this kind of awesome research. So it isn't just temperature and salinity, it's also these other sensors. and this little animation about how the floats actually work. It's really exciting. And I want to show you just how many people are involved. And yes, if you go to the SOCOM website, you can actually check out, we're kind of the pilot project for the global biogeochemical array, which is now funded just this last October by the National Science Foundation. It's through their mid-scale research infrastructure project. And it's so exciting, but I want to show you. So SOCOM is like the pilot project through polar programs for the Southern Ocean. And we're going to talk more about the global array, because although the Southern Ocean is important, and everybody who knows me knows how obsessed I am with that ocean, but the rest of the ocean is also critically important. And so the expansion of this array so we can do a global budget is the coolest thing ever. Don't take my word for it. I'm going to show you. All right. So, okay. I wanted to actually show deploying the floats in case there are people here who don't know how much work it is to get one of these CTD arrays over the side, fill up the bottles. Phoebe did a good job of describing how much extra work it is for all of the trace people who can't get anything dirty. But for all the rest of us, just regular oceanographers, it's still a lot of work. So you put that array over the side, you go all the way to the bottom, which is an advantage that we don't have with the floats because they only go 2 kilometers, not all the way to the bottom, although there is deep cargo coming online, which will help with that. But they don't have chemical sensors yet, so because crush depths, are a big thing. But all of this work where you pull the water back to the surface and make all these tiny little measurements, etc., it is hard. It is super hard work because this is and there is my student Becky, who's now a postdoc and research scientist at the Geophysical Fluid Dynamics Laboratory. Look at her muscling that puppy into the water. Okay, 2 days of ship time can get you about 4 profiles. And it costs about $100,000. The same one of these biogeochemical floats costs less than $100,000 and will do 250 profiles. 250 profiles for the same 100 grand instead of 4. Now we need our ships, and if I could get enough ships to do enough measurements, I would absolutely do it. But they're very expensive, and we don't have enough of them. And frankly, since the Cold War, we keep mothballing our ships and we don't replace them. So that was never going to work. So here are the deployments for SOCOM just from 2014 to 2020. You can see we started out with 0 of these biogeochemically censored floats. And ta-da! The global array of biogeochemical floats has now been funded by the National Science Foundation. I cannot tell you how thrilled I am. Look at all these beautiful stained glass window people who made it possible. You have no idea how hard they had to work to get this done. All over the country, they have been working. It is amazing. Oh, my favorite people. Okay, and here's where we are, like this month. Okay. We have 410. Not all of them have all the right sensors. All the NSF ones do, but there are others that have been put in by our international partners, some of which don't have all the sensors. And this was us in Villefranche in France actually hammering out what kinds of sensors would be on these floats as we collaborate with our international partners to get more of these in the water. And we're getting air seep carbon flux from the floats. That's Alison Gray there and her first amazing paper showing all of these float trajectories and how we are watching in real time our planet take up that carbon, our ocean take up that carbon. We're also watching carbon come from the deep ocean. You can see in this one coming up to the surface, spiraling upwards. And you can see all of the red dots over here is actually outgassing of carbon from our deep ocean. The rot of ancient ages is coming to the surface through that increase in wind. It's very scary. I really hope we choose as humans to target one of those lower trajectories because I'm worried about the feedbacks from our ocean if we don't. We are assimilating all of that data into what was the physically based Southern Ocean State Estimate, and now the biogeochemical Southern Ocean State Estimate, where data assimilation of all of this biogeochemical data nudges us towards truth, towards real time. It's so exciting, from which we can do forecasts. This is projections published in Nature and Nature Geosciences on the importance of wind and meltwater for the observed chemical and physical changes in the Southern Ocean. We've already improved the models. I know, woohoo, look at this. gangbusters. And if we don't improve the models, this is what happens. The new AR6, the brand new models that just came out, that have just been written about by the IPCC, there is a 100 petagram of carbon difference in how much the Southern Ocean takes up of carbon over the next, through 2100, which is only 80 years from now. And that is equivalent to 50 ppm in the atmosphere. Can you imagine how important it is to get this ocean carbon uptake right? It's more important than how much we burn, almost. I'm really quite serious. So we've made progress towards near real-time carbon accounting by improving our ocean system. We didn't have a Supreme Court ruling. We didn't have an international political agreement. We didn't have carbon observing satellites. We didn't have Earth system model prediction. We didn't have carbon sensitive floats. Yes, we didn't. Now we have all the pieces. This is where we are headed, is this vision of watching, seeing, discovering what the breathing of our ocean and how it is helping or hindering us. And so what comes next? We're going to continue to build out this carbon observing and prediction system. We're going to complete implementation of near real-time carbon accounting. We're going to publish the top 10 economies' monthly carbon impact and save the planet, or at least the humans. That's what we're going to do. So thank you for watching, and I appreciate your time.
Thank you so much, Dr. Russell. Does anybody have any questions for Dr. Russell? I'll just say I really appreciate your enthusiasm. You've been working at this for so long, and it's absolutely amazing to see you so excited about something that is huge for both your discipline and the world in general.
We're changing the world. What was invisible to most of our 7 billion is now put on the float, pops its head above the water, relays its data by Iridium satellite, and is put on the global telecommunication system like that. Not informing our operational centers, informing our ocean forecasts, our weather forecasts, and eventually we'll be informing our carbon accounting. Here we go. This is how microsensors and better batteries help us change the world and put us in the driver's seat. What information that helps us make wise decisions about that vast, vast ocean, which most humans have a really hard time imagining how important it is to us, every single person. So yes, I have my dream job. Thank you very much.
Yeah, and I absolutely loved going to the sea when I was doing that, but those ships cost a fortune to operate, and they just don't cover that much space. So these remote sensing options and floats are absolutely amazing.
People
got a question. Oh,
yes,
go ahead.
People don't realize that the law of the sea is why floats. They'll all say, well, why don't you just get an AUV or something? One, they're way more expensive and they don't last as long, and they require more people time, right? But two, the law of the sea, it says if you drive it into somebody's exclusive economic zone, you need a permit every time. But if it drifts in, it's legal. Hello floats. And hello the UN, UNESCO, and the IOC approving this. These floats and these sensors are approved for use by the International Oceanographic Commission. So the whole world has agreed that this is important information, and they're willing to let all these floats operate, and we freely share every bit of the data to help the whole world.
Again, yeah, that open data is really important. So one of the questions, so in terms of geoengineering and how this can inform geoengineering, are these measuring by carbonate measurements, carbon sinks?
No.
So about how deep are they going?
They're going 2 kilometers, which is most of the active ocean. Full stop. Second, we're doing inventories, basically, because we assimilate all this data into ocean models, and that then allow us to do near real-time budgeting, or forecasting with initial conditions. So essentially what we're doing is reducing the uncertainty and using every scrap of data, whether it's the nitrate sensor or the oxygen sensor, the pH sensor, which gets us to the carbon system, salinity, temperature, and then the optical sensors that help us with the validation of the chlorophyll measurements that we're making from space, because you do need some in situ data to really be sure you're looking at how much biomass, right? How much of that is actually carbon and not just a quote unquote optical illusion.
That actually ties in really well to the next question, which is, are you using satellite data in partnership with these floats to kind of complete the picture, the global picture?
Of course we are. In fact, this data is what we're using this to do observing system design. We think we need more wind measurements. The surface vector winds that are required to do the kind of simulation you see behind me we're only getting basically we have like set between the international community, they've basically phase locked all of our scatterometers together. So we're only getting about 2 measurements per day per location. If you see these great big huge storms behind me, that's not enough. We need at least 4 in order to really capture the nonlinear effect of these big storms on that deep ocean carbon that may be outgassing. And everybody knows, right, that carbon dioxide went up in the atmosphere even under COVID conditions. The lockdown didn't slow it down, which means our natural feedbacks are kicking in. I don't know about you. I have kids and I'm scared. I think we need to do this sooner. The science must accelerate to get in front of the change. Right now, even with all we're doing, it's not going fast enough. I really wish Congress would give you a whole bunch more money to do this, National Science Foundation and NASA and NOAA. Please, please, please. We promise we'll put it to good use.
We'll never say no to an increased budget. Well, thank you so much for sharing that. It's fascinating to learn about the floats.
Thrilled to be here, and thank you guys for all your hard work, especially through pandemic. You know, we were still deploying floats because the National Science Foundation didn't go to sleep. I'm so grateful, I can't tell you, because we would have had a floats in our network without your help. Deeply appreciate it.
We're happy to serve the scientific community. Yeah, so as Chris pointed out in the chat, thank you to all of you who are in Europe and Asia who are still with us. It's very late there, we understand that. That being said, let me introduce our final speaker for today, Dr. Chris Parsons, who's going to be telling us about the National Deep Submergence Facility. Dr. Parsons has been involved in marine mammal and marine conservation research for over 2 decades, as well as being involved in projects on every continent, including Antarctica. He's currently a AAAS Science and Technology Policy Fellow working in NSF's Division of Ocean Sciences. He was originally an associate professor at George Mason University here in the States, as well as their director for the undergraduate environmental science program. His claim to fame is that science fiction writer Douglas Adams gave Chris his old typewriter on which the author wrote Hitchhiker's Guide to the Galaxy. So without further ado, go ahead, Chris.
Can you see my screen okay?
Yep, good to go.
Okay, great. So Joanne was talking about going down to depths of 2 kilometers. So I'm going to take you even deeper. I'm going to talk about some of the deep sea research that NSF funds through the National Deep Submergence Facility. So as Joanne mentioned, the oceans cover 71% of the Earth's surface. But the ocean actually houses 99% of the world's biosphere, the area in which living organisms are found, which us marine biologists and oceanographers know how important the oceans are. But most of this biosphere is actually a deep ocean environment where it's pitch black, the temperatures are just above freezing, and also subject to crushing pressures. To give you an idea, at the bottom of the Mariana Trench, the pressure is 16,000 pounds per square inch compared to 14.7 in the average home. So absolutely crushing pressures. It's the equivalent of an elephant walking over you if that elephant is wearing stilettos. The ocean has an average depth of approximately 3.7 kilometers or 2.3 miles, or 347 school bus lengths. So you need special equipment to visit the vast majority of the ocean, which is why less than 5% of the seabed has been explored and mapped in detail. So the National Deep Submergence Facility, or NDSF, is funded primarily by the National Science Foundation, along with the Office of Naval Research and NOAA, National Oceanic and Atmospheric Administration in order to allow us to research these deep ocean areas. It provides essential equipment for reaching the deep ocean that it makes available to scientists in the US, enabling important science to be conducted. Probably the most famous part of the NDSF is the submersible Alvin. So Alvin's capable of diving to depths of 4.5 kilometers or just under 3 miles, able to explore 68% of the sea floor. The Alvin is crewed by 3 people and allows scientists to gain this unique face-to-face, first-hand knowledge of what the deep sea environment looks like. Here's one of the pilots of the Alvin. In fact, Cindy Van Dover is the first female Alvin pilot. And recently we had Dr. Dawn White, the first female African-American Alvin crew member. So scientists can go down in Alvin and actually get to see the ocean depths face to face. Alvin's currently undergoing an upgrade which will allow it to be able to dive down to 4 miles, allowing it to explore 98% of the sea floor. Now, you may have famously seen Alvin exploring this famous ship, the Titanic. So Alvin went down to 2.37 miles and took some of that amazing footage of the Titanic actually in the ocean water, which features prominently in the movie. They also used this mission to the Titanic to test a remotely operated vehicle, or ROV prototype, that they called Jason Jr., that was attached to Alvin and allowed them to actually explore inside the Titanic, taking amazing photos, which you see in the movie, of the great staircase, of bedrooms in the ship, getting into places that would be too small or too risky for Alvin to try to attempt to look at. As a result of using Jason Jr. as a prototype, they developed a new type of remotely operated vehicle, Jason. And then eventually in 2002, after Jason was retired, Jason 2 was launched. So Jason 2 is still operating at the moment, and it collects amazing underwater footage, video footage. Medea acts as a shock observer for Jason. So Medea is attached to the support ship, and then Jason is attached to Medea. So this allows that if it's rough, stormy weather at the surface, Medea acts as a stabilizer or as a buffer, so that Jason isn't dragged around the ocean seabed by the movement of the ship above. It also has camera equipment which allows it to video Jason as Jason goes off into the ocean depths. So together, Medea and Jason can go down to a depth of 6.5 meters. And it has a 10-kilometer or 6-mile cable, allowing it to explore these great ocean depths from the comfort of the Jason's control room. So instead of being in a cramped submarine, you can be sat in the nice, warm, cozy control room, observing what Jason is videoing, while, as you can see here, someone's having their lunch and a cup of coffee. In addition, Jason has manipulator arms, which allows it to collect geological and biological samples from the deep ocean and then bring them back to the surface. Here's Jason collecting some samples from a deep-sea hydrothermal vent that would be too dangerous for a submersible to approach, because those temperatures are about 400 degrees centigrade coming out from that hydrothermal vent. So a submarine passing into that would suffer some serious damage. So Jason can approach these dangerous areas. Finally, there's the autonomous underwater vehicle Sentry. So basically a programmable deep-sea robot. You put data in as where Sentry wants to go, where we want Sentry to go, and off it goes, videoing, collecting sonar data, and so on of the deep sea environment. It has magnetic sensors, it has a number of sonar systems, allowing it to map in detail the ocean bottom, and it can dive to about 6 kilometers. One of the important projects that the NDSF was working on recently was highlighted when they discovered evidence of drums of the toxic pesticide DDT that had been dumped off the coast of California. Now, there is a permitted dump site that these drums were supposed to be placed in, but basically they discovered that they were just illegally casting off these drums into the ocean willy-nilly, and sometimes even shooting the drums with machine guns, filling them full of holes so that they would sink, leaking out DDT. So Century surveyed the ocean bottom, discovered these drums, and then Jason went down to collect samples of the contaminated seabed around these drums to check that it was indeed DDT. They discovered that many of these barrels had been broken open or showed signs of leakage, and they even found bullet holes in some of the drums because, as I mentioned, this was one way they got the drums to sink. They shot them with machine guns. Now, the domestic use of DDT was banned in 1972 because of concerns about the impact of this pesticide on the health of humans and also wildlife, famously highlighted in the book by Rachel Carson's Silent Spring. But before this ban, one of the largest producers of DDT internationally was based in Los Angeles County, California, and they were allowed to dump DDT waste off the coast of California. And they dumped between 2,000 and 3,000 barrels of DDT-related waste every month at sea for 20 years, totaling approximately 1 million gallons of contaminated waste each year. The NSF-funded discovery found that there was wide-scale DDT contamination of the deep seabed over a 3,000 square kilometer area, with levels of DDT and associated chemicals up to 160 times greater than the levels at which toxic effects may occur. And they're seeing these toxic effects of DDT throughout wildlife off the California coast, in particular in sea lions. Sea lions off the coast of California have been found with very high levels of DDT, and these studies by the NDSF have helped to highlight where this DDT is coming from. And this DDT has been impacting the immune systems of the sea lions. It also affects the reproductive system, so they are producing less offspring. But in particular, the immune system, the effects of DDT has is kind of like HIV/AIDS. It reduces the immune system, which makes these animals much more susceptible to getting diseases, which is why we've seen so many stranded sea lions off the coast of California. The researchers described the way these toxic materials were dumped off the Californian coast as inherently sloppy. And recently, there has been a congressional review of this DDT dumping, and the Californian government is trying to develop a plan in order to try and mitigate and remedy this contamination. The NDSF was also involved in investigating the impacts of the Deepwater Horizon oil spill. Funded by NSF's Rapid Response Research Program, Century and Alvin went down to investigate the impacts of the oil spill on deep sea ecosystems, in particular, the impacts that the oil was having on deep sea corals. The NDSF has also made other deep sea discoveries, famously discovering hydrothermal vents, these hot water outflows which have unique ecosystems around them in temperatures that scientists thought that life couldn't possibly exist. And they discovered these off of the coast of the Galapagos. Now we know that there are hydrothermal vents in various parts of the world. And in fact, NASA has been very interested in this research, sometimes borrowing Alvin and the equipment of the NDSF, because they think that this might be a way that life could possibly exist on other planets in the solar system. So looking at these hydrothermal vents give them ideas of what exobiology or biology on other planets could potentially look like. For example, the moons around Jupiter. And who knows what else the Alvin and Jason and Sentry might discover in the future. Maybe they'll discover the remains of some sort of underwater city off the coast of the Mediterranean. Who knows? But certainly the video footage and the sights and sounds of these deep sea explorers hopefully will encourage young viewers to pursue their own deep ocean adventures one day. Certainly, I know that I was very influenced by seeing video footage of Alvin and other submersibles when I was a kid to want to get involved in oceanography and marine biology, so that one day maybe I'll be able to go in a submersible myself and see these amazing deep ocean ecosystems as well. So for more information on the NDSF, you can go and visit their website, the Woods Hole Oceanographic Institute, and I'll just leave you with this video.
Thank you so much for sharing, Chris. We've got a few questions, one of which I'll provide some context to. But the first one, so this is something you're well versed in, I know. You're talking about the deep sea, and we see these these creatures portrayed in media and everything. Are they real? Do they actually reflect what's down there? And a second follow-up question to that is, like, if you go down, how safe are you actually in those subs?
Well, let's start with the last question first. Actually, very, very safe, because these submarines are extensively tested. You're basically sitting in this really, really thick titanium ball surrounded by the rest of the submarine. So even though they go diving down to, well, the Alvin will soon be diving down to 6 kilometers, they can actually go much, much deeper. So there's quite a big area of a margin of error there. So they can go incredibly deep. And, there are also submersibles now that can go down to the bottom of the Mariana Trench at 11 kilometers as well. And the things we see on the TV in terms of the deep sea organisms, well, they definitely do exist. However, they tend to be quite widely distributed, and very often are in the sort of patchy little deep sea oases. So, for example, around hydrothermal vents, there'll be a lot of life there, and then there'll be not much for quite a distance. And then you'll find a carcass of a whale that has fallen to the bottom of the ocean, and that will be surrounded by all sorts of deep sea organisms like hagfish and sleeper sharks and a variety of different species. So there's a lot of ocean down there, and there's lots of really cool, weird species. But for a lot of the ocean bed, it's things like crinoids and brittle stars and urchins and flatfish and things like that. And occasionally in the deep ocean, you'll find these amazing weird things like gulper eels. Although one of the highest amounts of biodiversity in terms of the oceans are what are called lanternfish. And they are found a couple of kilometers down, and they migrate up to the surface at night, and then they go back down into the ocean depths during the day. So they actually make up a huge mass of marine species.
I actually did some research on them when I was still in school. Another question, so something I posted in the chat that I want to highlight, that's very relevant to what Dr. Parsons just talked about, is a recent example of what happens when things sometimes go wrong with submersibles. So Dr. Bob Ballard, who discovered the Titanic, founded the Ocean Exploration Trust. And one of their initiatives is the exploration vessel Nautilus, which goes out and does deep sea submersible sampling and live streams it on YouTube. And recently, they have two submersibles, unmanned, Hercules and Argo. Argo is the main submersible, and Hercules is a small one that kind of sits just above it that acts as a buffer. So, the ship is going up and down with waves. You don't want to jerk on the cable of a very expensive rover. So they have Hercules that sits on top. And something went wrong during one of their missions, and it actually sunk to the bottom of the seafloor. Luckily, there were nearby ships at the time who had their own submersible, who were capable of showing up within 2 days. They knew exactly where they were. They launched Jason, so Jason 2, one of the ones that Dr. Parsons just mentioned, and recovered it very well. And they're in the process of repairing what needs to be repaired. But it was this huge, very quickly established collaborative effort between NSF-funded vessels, WHOI, which is the Woods Hole Oceanographic Institute, NOAA, the National Submergence Facility, and the Ocean Exploration Trust, among just a few of their partners that all quickly came together to go offshore and rescue these really critical ROVs. So I posted a link to how that happened. But one of the questions that I was just looking back through is, so they rescued Hercules and Argo. Jason also has its own mini float called Medea that sits above it. And the question is whether they used Medea or not on that dive. And I'm struggling to, I don't think they did. I don't recall any widescreen footage of the rescue. And when I watched the whole thing, when they pulled up Jason, I don't remember them pulling up a smaller submersible first. Chris, do you remember?
Yes, I don't know. I know that we have a link on NSF Twitter about the rescue, but I'm not sure if they use both. If they use the entire system, then the entire sort of 10-kilometer cable, then they do use both. So I'm not sure about that, I'm afraid. Have to look that up.
What I just posted is a video that the Nautilus team put out that kind of summarizes what happened during the rescue. So you don't have to watch the several days worth of footage that they recorded.
As Joellen mentioned, there's only about 6,000 oceanographers. So it's a pretty small community, like everyone knows everyone.
Oh, we actually
that's part of the collaboration.
We just had confirmation from one of the NSF program officers who's in charge of infrastructure and facilities that Jason was working in single body mode, so Medea was not down there.
Okay.
Which makes sense because they were worried about entanglements. And it's one less thing you have to worry about. So thank you, Brian, for that. Another question that it's often stated that most of the life on Earth, so 50 to 80% of all species, are in the ocean. Do we have the studies, that reference or that show that the statement is true? and what more about the composition. So I think you mentioned lanternfish are a huge percentage of life that nobody really knows about.
That's true, yeah. In terms of biomass, the lanternfish are one of the highest amounts of biomass. And in fact, when they first started doing sonar studies, they saw this strange sort of false seabed that was showing up on the sonar, which actually this thick, dense layer of lanternfish. In terms of mammals, the largest number of mammals are actually crab-eater seals in Antarctica. 50 million or so crab-eater seals. So in terms of the ocean, the amount of biodiversity in the ocean is actually quite incredible. We often hear about the Amazon and rainforest being really high in biodiversity, but now we're actually starting to study these deep ocean areas. We're finding some of these deep ocean areas are as biodiverse, or in fact more so sometimes, than the Amazon rainforest. So there's been a bit of a bias from all these studies in places that are easy to study, like forests and so on. Now we're actually studying the deep ocean. We're finding out quite how many species there are down there in areas where they thought life couldn't possibly exist. And as we study more, we'll undoubtedly find more and more species. Although, as I said, the really sort of deep ocean, the life is a bit spread out, but because it's such a huge volume, if you added it all together, it becomes really substantial.
One last question, I think, to finish us off, and you can put your marine mammal hat on for this one. How much do you think we'll be able to learn about the lives of beaked whales in the future? So what technological advances do you think we need to better understand and protect these little-known marine mammals?
Really good point, because beaked whales often, to detect them at the surface, it's been calculated you've got less than 1% chance of actually spotting them at the surface, because they go up, they breathe, and then they just sort of hover about 20, 30 meters underneath the surface and then dive down. They've just discovered recently down to about 3 kilometers, which is really new data. And they've been finding out this because they've been able to go up to beaked whales and attach tags to them that have collected data. So I envisage that as these tags get sort of smaller and smaller, and they can put more and more electronic gear on, then we'll find out more about what they're doing under the water. I don't see why they couldn't have some sort of video type footage. They've tried this with sperm whales, where they tried to put video cameras on sperm whales. The idea being that maybe they'll get to see a sperm whale attacking a giant squid in the deep ocean. But what they found was that the sperm whales would just sort of stop and then just knock the cameras off, because they were quite big and quite bulky. So as the technology gets smaller and the video, the types of video that we can collect get more sophisticated, so we could get low intensity light video collected, for example, I'm sure we're going to get really cool underwater video footage of beaked whale behavior in the near future. With these larger videos, you have to have lights on them, intense lights, in order to get the video footage, and that's going to change their behavior, because they're basically swimming around with a big spotlight, and you're not going to get natural behavior. So maybe they can put things in light frequencies that the whales can't spot, maybe like red light, and irradiate that, well, not radiate, that's the wrong term to use, but sort of light up the surroundings, collect really cool video footage of what beaked whales and sperm whales are up to. So I can see that happening in the very near future, because this tag technology is becoming really sophisticated now.
I think that's we'll end with questions.
Well, I guess I should say thank you very much to everyone who has tuned in and joined us. We've been recording this session, so we'll be putting the video up on the NSF website. We'll also be sharing this around to social media. And particularly thank you for all of those in East Asia, Africa, and Europe who are joining us in the middle of the night. Thank you very much for joining us there. And thank you very much for our presenters, Phoebe, John, Joe Ellen, and thanks to you, Lindsay, for introducing us. And have a good weekend.
Have a great weekend, everybody.
Recording stopped.